So let's go back and look at the Bohr model of the atom again. So we'd already looked at it a couple times here. And so we got, imagine an electron going around here, around the nucleus. And so now we want to look at this from a magnetic standpoint. So what's the magnetic moment of that electron? Because that actually makes a difference. Because if you apply an external magnetic field to the hydrogen atom, it's going to behave in a particular way depending on whether the field's one way or another way relative to the atom, or if the atom is oriented one way or the other. And so we want to look at this magnetically. So we know that there could be a torque on that electron orbital there, okay? If the torque is depending on how it behaves, the torque, it can be the magnitude of that is mu cross B, okay? There it is. So we need to know mu. What's the magnetic moment of that electron? Okay, so the magnetic moment of the electron, well, we know magnetic moment is NIA. Well, we've got one electron out here going around. So the distance, we're going to, R naught, that's the, or RB, that's the Bohr radius. Okay, so the Bohr radius, the effective radius of that electron's orbit out there, is 5.29 times 10 to the minus 11 meters. Now let me point out, really it's not an electron going around in an orbit. That's not the way this really is. But the amazing thing is that mathematically, if you work through the mathematics of it as if it were that way, it's actually kind of close to what really happens. Okay, so A is going to be the cross-sectional area of that. So that's going to be pi r squared. Okay, N is going to be 1 because there's one turn. Okay, now what is I? I is the current. So that's going to, the current's defined dq dt, or we can just think of it as the average current. It's just q over t. T is the period. Okay, well, if we imagine the electron is going around at some velocity v, then we would say that the period is going to be the distance around 2 pi r divided by the speed that it's moving around. So this would be, that means we could then say that Q is E, so that's going to be E. So this will be E times V over 2 pi r, where that V is not the voltage, that V is the velocity of the electron. Well, how do we find the effective velocity of the electron? Well, what keeps it going around? Well, what keeps it going around is centripetal force. What's pulling on it to make the centripetal force? The electrical force. So the centripetal force is equal to the electrical force. So mv squared over r, you remember that from physics 1, k sub b, q1, q2 over r squared. Well, that's going to be k sub e times e, so e squared over r squared. So that r cancels that. And so we can do a little bit of algebra and solve for v. V is going to be e times the square root of k sub e over mr. So the velocity is 1.602 times 10 to the minus 19 coulombs times k sub e, 8.99 times 10 to the 9th Newton meters squared per coulomb squared, divided by 9.11 times 10 to the minus 31 kilograms. And R turns out to be Bohr radius 5.29 times 10 to the minus 11 meters. Okay, so you work all this out, and we got Newton meter squared per coulomb squared. We got kilogram down here, cancels the kilogram that's in the Newton. Got a meter up here, cancels one of those. The coulomb. So what's all the stuff that's under the square root comes out to be meter per coulomb second. Okay. That cancels the coulomb that's up there, and so the answer comes out in meters per second. So it's 2.19 times 10 to the 6 meters per second. Okay, so now we're ready to put all this together to find mu. So mu, okay, is going to be equal to N I times Ni times A. So this is going to be equal to 1 times I, which we said was equal to E times velocity over 2 pi r, and then this is going to be equal to pi r squared for the A. That pi cancels that pi, that r cancels that r, and so mu comes out to be equal to 1/2 E times V times r. We now know what V is, so we plug that in there, and we get 1/2 times 1.602 times 10 to the minus 19 coulombs times the velocity, which we just figured out, which was 2.19 times 10 to the 6 meters per second, and then all that times the r, 5.29 times 10 to the minus 11 meters. So mu comes out to be equal to 9.27 times 10 to the minus 24 amp meter squared. And so that is the magnetic moment of that electron in the hydrogen atom. Okay. Now we'll get back to this whole thing later in the semester, because it turns out that that magnetic moment also relates to the angular momentum of the electron. Okay, because angular momentum is mvr, if you remember from physics 1. And so we know that mu is equal to 1/2 EV times r. Okay, so if we multiply both sides of the equation here by m, okay, and we notice that, in that case, the mvr is, so that means that's going to be 1/2 E times L. So L is going to be equal to 2m mu over E. Now, turns out the quantity m over E, or really what they calculated was E over m. You look in the book, E over m is a defined quantity. The charge per mass of an electron is a defined quantity. So that means that all of a sudden we just have a very nice relationship between the angular momentum and the magnetic moment. So we'll get back to that later, because it turns out that this angular momentum plays a key role in how the hydrogen atom works.